In this video, we're going to talk about the definition of the derivative of a function. Before we do that, we're going to go over the idea of slope, and you might remember from algebra that in order to find the slope of a line, we needed 2 points on the line, and then we could define that slope if we had the points a comma f of a and b comma f of b that were on the line, f of x equals mx plus b. Then we defined the slope of that line. We defined the slope of that line to be the change in y over the change in x. And the change in y is the change we have here is f of b minus f of a. Those are the two y values on the line of the points. So f of b minus f of a over the change in x. And so we look at the x-coordinates of the 2 points on the line, and that would be b minus a. And it was also good to remember that the slope of a line was always the same, no matter where you were on the line and what 2 points that you used on the line. So the slope of a line was constant. Okay, so now in calculus, we're going to move over to the idea of the slope of a curve, or the slope of the tangent line to a curve. And so ultimately, we might have, say, some general curve, y equals f of x, and we're interested in finding the slope of a tangent line. I just drew this tangent line. It could be any tangent line here. But the idea is the tangent touches the curve in precisely 1 point. And so therein lies the little riddle. How do we find the slope of a line that at one particular point, when in algebra we were taught that we needed 2 points? So what we're going to do, the basic idea conceptually, is that we're going to find the slope of a tangent line, is that we're going to find some nearby point to help us out. So if we call that point Q, we now can find the slope of a tangent line from P to Q. And we can use our formula in algebra. Make this a little thinner. In algebra, we had a change in y over change in x. So we have 2 points, and each of those points will have coordinates, so we could find the slope of that line. That line is called a secant line because it has 2 points. Okay, now this slope does not look much like this slope here of the tangent. You can tell this is much steeper. So let's see what happens if we try a point a little closer. You might notice that once we move this point a little closer, and we still stay with our point P, that the slope of this secant line, so we're kind of moving our point Q in a little closer to P, now it's a little bit closer to the slope of our goal, the tangent line. Let's try again, moving Q even closer. And as you might suspect, the closer we move Q to our point of interest, P, the closer our secant slope, or closer of this slope of this line here, equals the slope of our tangent. So eventually what we're shooting for is we want this point on the line, this Q, to continue to approach P until they're essentially the same. What we're basically saying here is that the limit of the slopes of the secant line, approaches the slope of the tangent at P. This is the crux of the idea here, that eventually we can take our idea in algebra that we have the slope of a line is determined by 2 points, and then we can use a very important principle in calculus, the idea of taking limits, to consider the limit as this point Q slides along the curve closer and closer to P, generating or resulting in the limiting of the secant lines approaching a particular tangent line. Okay, so mathematically, I've taken the liberty of constructing the graph here. Let's take a look at this graph piece by piece. So here is our graph of y equals f of x. And we're going to start with our point, this is our point P. And P has the coordinates x comma f of x. We're just picking x. And so on the curve, the y coordinate is f evaluated at x, because we're along the blue curve. And then what we do is we go out just a little bit, just a little distance. This is delta x. We can also call it h. So we're going out a little positive distance away from x, call it h or delta x. Some books might use delta x. Okay, so x plus h is this new x coordinate, and the y coordinate on that point, on that graph, is the x coordinate, x plus h, and f evaluated at x plus h. This is essentially our Q. So all we've done here is we've said, okay, P is x comma f of x, and Q is some nearby point on the curve, and algebraically, we just added a little bit to it, so we say x plus h, that's adding a little bit to the x coordinate, and then on the y coordinate, we evaluate x plus h, we evaluate the function f at x plus h. So now we're set to go. So the y coordinate of this point Q is f of x plus h. The y coordinate of this point P is f of x. And so we want to find the slope of this secant PQ. The slope of the secant PQ is equal to the same thing as we had in algebra. It's the change in x over the change in y, where the change in y, change in y over the change in x. The change in y is, this is the first y value, f of x plus h, minus f of x. So our change in y, this distance right here, is the change in f of x plus h minus f of x over now our change in x, which is simply x plus h minus x. Okay, this can be slightly simplified, where the numerator is still the same, f of x plus h minus f of x. And then if you notice, the x's cancel. X plus h minus x. So these x's cancel. And we're left with h. This is our slope of the secant line from P to Q. Okay, now what we want to do is consider the limit, because the idea here is we want to consider Q approaching P, or another way of putting that is the difference between these two x's is getting smaller and smaller and smaller. So that means that h is going to approach 0. So what we want to do here then is consider, mathematically we can write that as the limit as h approaches 0 of our formula for the secant. That's f of x plus h minus f of x all divided by h. Now this limit is a very important limit, and it's what we actually define. Well, this is, first of all, geometrically, this is the slope of the tangent. But mathematically, we define this also as the derivative of f. And we can write that, there's a special notation for it. The derivative of f we can write as f prime of x. Sometimes you might see it as df over dx, which is read df of dx. And so basically what we've done here is we've shown mathematically that if we consider the slope of the secant line between 2 points, 2 distinct points, and we consider the limit as one point approaches the other, then we end up with the slope of the tangent line, and that limit has a very important, this limit expression has a very important application all throughout differential calculus. And so we give it a special name called the derivative of f, and it's written f prime. So you might be asked in practice, and I'll do this, I'll actually solve a couple of these in our next example, but in practice you might be asked to find f prime of x using the limit definition. And what that means is you might be given f of x. You'll be given some formula. It could be f of x equals x squared. Then you need to find f prime of x using this limit definition. The limit as h approaches 0 of f of x plus h minus f of x all over h. So in the next video, I'll go over a few applications or a few examples, including the f of x equals x squared example that I just mentioned here. In the meantime, I hope this helps you get a general idea of the definition of derivative.